Hi guys, this is Dr. G here, and in this particular video we will talk about aromaticity and the Huckel rule. So in my previous video I basically discussed the structure and stability of benzene, right? So in there we discussed the structure of benzene and we learned that benzene is a monocyclic ring, okay, with 6 carbons, right? It has a 6 carbon monocycle, and then it has three uh, pi bonds, or in other words it has 6 pi electrons, right? So we learned that it is a planar structure. Why? Because it all the 6 carbons are sp2 hybridized. When carbons are sp2 hybridized, okay, the carbons are going to have a trigonal planar geometry. Okay, so benzene is basically a planar hexagon, okay, and it is sp2 hybridized, so therefore bond angles are approximately 120 degrees, okay. And also we learned that these 6 pi electrons are not going to be fixed. They are not going to be situated among 3 double bonds. Instead, these 6 pi electrons are in a more dynamic structure. They are more conjugated between all 6 carbons. Because of that, you can't pinpoint and then say, okay, these 2 carbons have a double bond and the others have single bonds. You can't say that. Instead, what you could say is that at any given point of time, the 6 pi electrons are equally distributed among the 6 carbons. So all these 6 pi electrons are conjugated among the 6 carbons. So therefore, when you take a look at the bond length, it is neither the size of a single bond or a double bond. It is actually kind of like a 1.5 bond or a 1.5 bond, because the bond length is approximately between a single bond and a double bond. So the bond length is around 139 picometers. And also we learned that benzene is extremely stable. Okay, benzenes do not undergo reactions easily. The reactivity is low, which means stability is high. In chemistry, we learned that reactivity and stability are inversely proportional. So if a molecule is less reactive, that means it is more stable. So benzene is very less reactive as compared to a hypothetical cyclic triene, because it doesn't undergo addition reactions very easily, or it usually don't undergo the reactions that alkenes display. And also when we take a look at the heat of hydrogenation, we learned that as compared to a hypothetical cyclic triene, it is 150 kilojoules per mole more stable. This stability is actually derived from aromaticity, okay. Or in other words, we can say because of the structure of benzene, okay, having a conjugated 6 pi electrons is a reason why this benzene has a very stable structure. So we can attribute the stability of benzene to aromaticity. So in this video we are going to talk about the aromaticity in more detail. So aromaticity, when we talk about aromaticity, we have to learn a rule called Huckel rule. Okay, so this rule basically defines what aromatic molecules are. So as you can understand now, benzene is not the only aromatic compound. Okay, there are many more aromatic compounds in organic chemistry, and basically Huckel rule helps us understand these other aromatic compounds. Okay, other aromatic compounds. So in this Huckel rule, or we call it 4n+2 rule. Okay, so in this 4n+2 rule, there are few checklists that molecules need to fulfill in order to become an aromatic compound. Okay, so first of all, you have to have a monocyclic system. So the molecule has to be monocyclic. That is one. And not only that, the molecule also has to be planar, which means, it is better to have carbons with sp2 hybridizations, right? Because sp3 hybridization, carbons basically have what? Tetrahedral geometry. So tetrahedral geometry is not planar. So if you want to have planar geometries for carbons, you have to have sp2 hybridization. That is a better hybridization than sp3. Okay, so and also you will need conjugated pi electrons, okay, conjugated system. So you have to have pi electrons that are conjugated, so they should be moving from one bond to the other, okay. The pi electrons should be conjugated, and those are the first three checklists. But the most important checkpoint will be the number of pi electrons. The most important point will be the number of pi electrons. Okay, so according to Huckel's rule, if a molecule is an aromatic compound, it has to have pi electrons that are going to be a solution for 4n+2. Okay, if a molecule is going to be an aromatic compound, it has to have pi electrons that are going to be equal to a solution of 4n+2. So this n could be any integer, okay. This n could be any integer. It could be 0, 1, 2, 3, anything, okay. So let's take a look at this 4n+2 in more detail. So if n is equal to 0, then the pi electrons will be what? Then the number of pi electrons will be 2. If n is equal to 1, then the number of pi electrons could be 6. If n is equal to 2, then the number of pi electrons is what? 10 electrons. Similarly, when you have pi electrons that are equal to 2 or 6 or 10 or 14 or 18, and it goes on, okay, then that molecule could be a candidate to be an aromatic compound. So let's revisit the Huckel rule. So according to Huckel's rule, a molecule could be considered as an aromatic compound if that molecule has a monocyclic ring which is planar, and it should have a certain number of pi electrons that will fit one of the solutions for 4n+2. Okay, so you have to have conjugated pi electrons that will fit a solution for 4n+2 equation. So when a molecule fulfills all these checkpoints, that molecule could be considered as an aromatic compound. So it doesn't have to be only benzene, okay. There are many other molecules that could fulfill this checklist. All right, so let's take a look at benzene again, okay. So benzene, if we take a look at benzene, we know that it is a planar ring and it has 6 pi electrons, and also it is a monocycle. So it has 6 pi electrons, it is planar, and it is a monocycle. And all the 6 pi electrons are conjugated, and it is conjugated. How do I know it is conjugated? Because the pi electrons are alternating, okay. So they can easily move between two carbons to the other two carbons, okay. So it is conjugated, so the pi electrons can be moved around, okay. That is why we call it conjugated, okay. So the pi electrons can move around. All right, so if a molecule is planar, monocyclic, but if it only has pi electrons that will fit the equation 4n, then it is considered to be anti-aromatic. This is considered to be anti-aromatic. Let's take a look at cyclobutadiene, okay. It is a monocycle, and then it has conjugated double bonds, okay. That means they are alternating, okay. They are alternating double bonds, and then the number of pi electrons is what? 4, because you have two double bonds, each double bond is what? 2 electrons. So multiply it by 2, you have 4 pi electrons, okay. So in this molecule you have 4 pi electrons, so it fits 4n and not 4n+2. So 4 pi electrons is a solution for 4n, okay. So therefore this is considered anti-aromatic. Cyclobutadiene is considered to be anti-aromatic, okay, anti-aromatic. All right, so I hope you understand the aromaticity now. So let's learn how to apply this, okay. So let's learn how to apply this. So a molecule like the previous one, cyclobutadiene, the same molecule, okay? Since it is anti-aromatic, it is not stable. Aromatic molecules are stable. If it is anti-aromatic, they are always unstable. That means they have high reactivity. Okay, remember, stability and reactivity are inversely proportional. If a molecule is unstable, it is highly reactive. It is highly reactive. So this diene, okay, this diene is extremely reactive. It even react with its own molecules, okay, its own kind at minus 78 degrees. So it will basically self react at very low temperatures. That means it is extremely unstable. Why? Because of the anti-aromaticity. But benzene is extremely stable. Why? Because it is aromatic. So benzene will not even show regular alkene reactivity. It is even less reactive than alkenes. Okay, it is even less reactive than comparative alkenes. So if a molecule is aromatic, it is going to be very stable and less reactive. If a molecule is anti-aromatic, it is going to be highly reactive. It is going to be highly reactive. So here's another example for an anti-aromatic compound. Okay, in here you have 4 double bonds. Okay, if you have 4 double bonds, you multiply it by 2. That means you have 8 pi electrons. You have 8 pi electrons, which is a solution for 4n, not 4n plus 2. 4n means what? Anti-aromatic. Not only that, this cyclooctatetraene, okay, this molecule is also not planar, and it is also not planar. Because of all these reasons, this particular compound will not be an aromatic compound. It is not a planar molecule. It does not have 4n plus 2 number of pi electrons. Instead, it has 4n number of electrons. So because of those reasons, it will not be an aromatic compound. It will not be an aromatic compound. But of course, it is conjugated, but it doesn't really matter. Even though it is conjugated, it will not be an aromatic compound. All right. So briefly, you can also explain aromatic stability using molecular orbital theory. Okay, so when you calculate energy levels of molecular orbitals for cyclic conjugated molecules, it will always show that there is always a single lowest lying molecular orbital. Okay, you will always start with a singest lowest lying molecular orbital, and above that you will have degenerate molecular orbital pairs. You will have degenerate molecular orbital pairs. Okay, so the lowest lying molecular orbital will have 2 electrons, and then after that the degenerate orbitals will have 2 electrons each. Okay, so a total of 4 electrons on the second and third molecular orbital. Okay, so we have already learned about molecular orbital diagram for benzene. Okay, so basically this is the molecular orbital diagram for benzene. Benzene has 6 pi electrons in 6p orbitals. Okay, and then when you put one lowest lying molecular orbital, and then after that everything else is degenerated. Okay, and the highest one will be only one molecular orbital. Why? Because you already used 5, and then this is the 6th one. So as you can see, when you fill electrons, this aromatic compound will only have 6 bonding electrons. This is bonding. Okay, these are bonding molecular orbitals. So all 6 electrons will be on bonding molecular orbitals. All 6 electrons will be on bonding molecular orbitals, and these will be what? Anti-bonding. You will not have any electrons. Okay, you will not have any electrons on anti-bonding molecular orbitals. So this molecule is stable. This molecule is stable. So if you have troubles in drawing these molecular orbitals, I can show you a trick. Okay, I can show you a trick. What you can do is you can actually draw the benzene molecule. Okay, let's draw the benzene molecule, but I want you to draw it pointing down. Okay, so this is pointing down, right? This is the downward point. And then when you are drawing molecular orbitals or energy levels, so this is the first one, second, third, fourth, fifth, sixth. And then once you have the molecular orbitals, every carbon will get a molecular orbital. Okay, and then you can simply erase the carbon-carbon bonds. So this will be the molecular orbital diagram for benzene. Okay, benzene, and of course in the middle you will have the non-bonding level. Okay, this line is the non-bonding level. Okay, and then below the non-bonding level are bonding. And then on top you have anti-bonding. Okay, in here you have anti-bonding molecular orbitals, and then you only have 6p orbitals. You only have 6p orbitals. I mean 6p electrons, excuse me. You only have 6p electrons. So start with the lowest level, 2, 3, 4, 5, 6. So all 6 of your pi electrons will be in bonding molecular orbitals, making this benzene an extremely stable molecule. Okay, so that is how you draw them. All right. I have a simple worked example in this slide. I want you to pause the video and then see if you could do this by yourself. Okay, see if you could pause the video and try this. All right, according to this worked example, to be aromatic, a molecule must have 4n plus 2 pi electrons. Okay, good. And must have a pair of monocyclic systems of conjugation. Okay, sorry, have a planar monocyclic system. It has to be planar, it has to be monocyclic, and it has to have 4n plus 2 orbitals. Okay, I mean 4n plus 2 pi electrons. Explain why cyclodecapentaene has resisted all atoms at synthesizing this molecule. Okay, so when you take a look at cyclodecapentaene, okay, as the name implies, it has 5 double bonds, right? Pentaene means it has 5 double bonds. So if you have 5 double bonds, you multiply it by 2, you have 10 pi electrons. Here's the thing. So it has 10 pi electrons, which is a solution for 4n plus 2. Okay, so this checklist is good. Okay, so you have 4n plus 2 electrons, and also this is a 10 carbon ring. Okay, so it is a monocycle, and it is conjugated, of course, because you have the alternating double bond structure in here. So why is it, I mean, if it is this reactive, for some reason it must be not aromatic. So the only other remaining thing that needs to be achieved is being planar. And for some reason it seems like this cyclodecapentaene is not planar. And if you try to draw this molecule, okay, if you try to draw this molecule, you will realize that when you draw this, you will have 2 hydrogen atoms that are basically violating their personal space, or in other words, they are too close to each other. Because of these 2 hydrogens are very close to each other, the molecule will be twisted. So rather than being planar, this whole molecule will be a little bit twisted, making it non-planar. So therefore, even though it has 4n plus 2 number of electrons, because of these 2 hydrogens trying to occupy the same space, or in other words, they are violating their nuclear distance, nuclear radii. Because of that, in order to accommodate the 2 hydrogens, the ring will have to basically twist and turn, making it non-planar. That is why this molecule is not aromatic. So remember, when I give you questions in the exam, some people just try to count all the double bonds and then say, okay, it fixed 4n plus 2, so that is aromatic. No, always think about the other factors. Is it monocyclic? Sometimes you can have more than one cycle. We will talk about it later. But most importantly, is it planar? And are the double bonds, or are the pi electrons conjugated? Okay, those are the things that you have to worry about. All right, so in the next slide, as I mentioned earlier, to have a conjugated pi electron system, you don't have to always have neutral molecules. Okay, you don't always have to have neutral molecules. Instead, you can have cations or anions that can still extend the conjugation of pi electrons, and therefore these cations and anions can also make molecules aromatic. Okay, so here I have two prime examples. Okay, so in here I have an anion and also I have a cation, and both these compounds are aromatic. Let me show you why. First of all, if you count the pi electrons, this one has two double bonds. Okay, so 2 times 2 is 4 electrons, and then also it has a negative charge. Okay, negative charge counts as 2 electrons. So if you add everything up, it will be 6 electrons, which means it fits 4n plus 2 rule. So this is good when it comes to the 4n plus 2 rule. And then also, as you can see, these negative charges can help extend the conjugation. These negative charges can delocalize the pi electrons. So therefore, this is a monocycle and it is a planar structure. Why? Because these negative charges are also sp2 hybridized. Whenever you have a carbon with a charge, or a radical even, okay, they are no longer sp3 hybridized. Instead, whenever they have a charge, they will rearrange to a sp2 hybridization, and then the charge will be on the p orbital. Okay, so it is sp2 hybridized, so it is planar, it is conjugated, and it has 4n plus 2 electrons, so that is aromatic. So this one is aromatic. And same thing here. Okay, so you have a positive charge on this carbon, and still it is sp2 hybridized. Why? You only have 3 bonds, so this carbon will be sp2 hybridized, and the vacant positive charge or vacant orbital will be the p orbital. Okay, unhybridized p orbital. And then this positive charge can help extend the conjugation. This positive charge can help extend the conjugation. Let me show you how. So you can basically shift the double bond here, and then you will have the double bond here, and then this carbon will become positive. So these positive charges can also help extend the double bond or the conjugation. And if you count the pi electrons, you have 3 double bonds, so that will be 6 pi electrons, which is a solution for 4n plus 2. So that is also good. This is a monocycle, everything is sp2 hybridized, so that is a planar structure. And therefore this compound cycloheptatrienyl cation is an aromatic cation. Okay, so you can have negative charges or positive charges, so you can have anions and cations, and still they could be aromatic. Okay, they could still be aromatic. All right, so this is, in this slide, it basically explains how you make a negative charge and a positive charge. I mean, this is, you should be familiar with this material, but feel free to pause the video and read it if you don't know how the negative charges or positive charges are formed in organic chemistry. But I'm going to rush through this to make the video short. All right, so in here I have two compounds. Okay, I have a 1,3-cyclopentadiene, which is not an aromatic compound, and I also have cycloheptatriene, which is also not an aromatic compound. Why? Because both these things are not conjugated. I mean, these double bonds can't move anywhere else, they are fixed, so they are not conjugated. So definitely these two are not aromatic because there is no conjugation. But if you make a positive charge or a negative charge or a radical by removing a hydrogen or gaining gaining an electron, or things like that. Okay, so if you make an anion or a cation, they immediately tend to extend the conjugation. Okay, so whenever you have a positive or a negative charge or even a radical, they extend conjugations. But here's the thing, radicals will be 1 electron count. Okay, so the thing about radical is that it has a hard time in fulfilling 4n plus 2 rule. Unless you have 2 radicals in your structure, radicals have a hard time in fulfilling 4n plus 2 number of electrons, so they will not be aromatic easily. Okay, but whenever you have a positive charge or a negative charge, they are not only extending the conjugation, they will also have the capability to make it aromatic if the pi electron number is a solution for 4n plus 2. So if you take a look at this one, it only has 4 pi electrons. So 4 pi electrons is not a solution for 4n plus 2. So this is not aromatic. But if in here you have a total of 6 pi electrons, how? 2 here, 2 here, and 2 here. That is 6 pi electrons. Whenever you have 6 pi electrons, that is a solution for 4n plus 2. So this is aromatic. All right, same thing here. So in here, the cation will have 6 pi electrons. So this is aromatic. But the anion will have 8 pi electrons. How 8 pi? You have 3 double bonds, that is 6. And then the negative charge will again bring 2 more. So that is 8 pi electrons. So this is not aromatic. All right. So here's how you, this basically should further explains the aromaticity. All right, once again, guys. Okay, so if you have an anti-aromatic compound, they are going to be extremely reactive. Why? Because anti-aromatic compounds are unstable. Okay, so it is difficult to prepare, and even if you prepare them, they will instantaneously react and become something else. But if you have an aromatic compounds are very stable, so therefore it is easy to prepare them, and they will remain as is for a long period if you don't try to do vigorous reactions with them. Okay, so they will be stable for a long time period if they are aromatic. All right, so this is basically the same two ions that we talked about before, the cyclopentadienyl anion and cycloheptatrienyl cation. We learned that they are both aromatic, and in here you have the orbital picture so that you can see how the pi electrons are arranged. Okay, all 6 pi electrons are conjugated in this system. In here also, all 6 pi electrons in these 7 p orbitals are conjugated, making them aromatic. All right. So here's a worked example once again. I wouldn't expect you to, take too long to do this. Okay. You might want to pause the video and try this by yourself. This is a very easy example. The starting material is not uh, very stable because it is not aromatic. Okay, and the end product should be aromatic. That is why this reaction happens rapidly. See if you can explain it. All right, here is the answer, but try to explain it by yourself. Okay. Next up, we are going to talk about heterocyclic compounds that are also aromatic. Okay, so let's talk about aromatic heterocyclic compounds. All right, so the heterocyclic compounds are, of course, cyclic compounds that contains uh, other atoms such as nitrogen, oxygen, or sulfur. Okay, so these are very similar to benzenes or the other carbon containing aromatic compounds. Okay, so carbon is basically what it is in group 4a, so it only had 4 valence electrons, right? So it tries to make 4 bonds. Okay, so if you take a look at nitrogen, okay, nitrogen is from group 5a, so it has 5 valence electrons, and because of that you actually have a lone pair. This right here is called a lone pair. So you don't have to try to pair these two electrons. Okay, it is like a bond without anything attached. Okay, so you also have a lone pair. Okay, so basically carbon hydrogen bond can be easily replaced. A carbon hydrogen bond can easily be replaced by the nitrogen lone pair. Okay, so basically if your brain can substitute carbons and hydrogens in an aromatic ring with a nitrogen, then that is all you need to know. Okay, that is all you need to do. All right, so let's talk about this in a little bit more detail. Okay, all right, so let's take an example. The first example that we are going to talk about is called pyridine. Okay, pyridine. Okay, so just to show you the similarities, I'm going to draw the benzene. This is benzene, and I'm going to draw this carbon label. Okay, so basically what the difference between benzene and pyridine is that this carbon right here, carbon hydrogen bond, is replaced by nitrogen with its lone pair. Okay, so you can basically think it very mechanically, to be honest. Okay, all right, so in pyridine, one of the carbons of benzene is replaced by a nitrogen, and nitrogen will basically have the same double bond and the single bond just like carbon, but instead of the carbon and hydrogen bond you have the lone pair. You have the lone pair. So that is pyridine. You can pause the video and read this slide, okay, but this should be very straightforward. And then pyrimidine basically have two carbons replaced by nitrogen. So two carbons are replaced, or two carbon hydrogen groups are replaced by two nitrogens, okay. And in both cases, in both pyridine and pyrimidine, okay, in both pyridine and pyrimidine, this lone pair, okay, this lone pair electrons are not a part of the pi electron group, okay. Keep that in mind. This nitrogen is sp2 hybridized, and this lone pair is not a part of the conjugated pi electron. So now if nitrogen is like this, it has a double bond, it has a single bond, and it has a lone pair. So all these are in the same plane, okay, and there's only one electrons on that is perpendicular to these three things that are pi electrons. This is the pi electron, okay. So lone pair is not a part of the pi electron. The lone pair on nitrogen is not a part of the pi electron. Keep that in mind, okay. Very important, very important. So in both pyridine and pyrimidine, the lone pair is not a part of the pi electron ring. So when you are counting the pi electrons, just count the three double bonds. Just count the three double bonds. You have 3 double bonds multiplied by 2, you get your 6 pi electrons. Don't be the guy who's counting these 2 electrons, okay? Extremely important. And this is the orbital picture. I mean, you can take a look at it by pausing the video, but I'm not going to explain it in more detail. But once again, guys, I just want to highlight you. The lone pair is going to be perpendicular to the pi electrons. So these lone pairs are not a part of the pi electrons. But when you are talking about pyrrole and imidazole, this is pyrrole and this is imidazole. Their lone pair, okay, so pyrrole and imidazole, their lone pair is actually a part of the pi electron cloud, okay. It is a part of the pi electron cloud, okay. How come? Okay, how come? So here's the thing. The difference between pyridine, pyrimidine and pyrrole and imidazole is that in pyridine and pyrimidine, let me write pyridine here. If you take pyridine, okay, the nitrogen did not have hydrogen. The nitrogen has no hydrogen. No hydrogen, right? But pyrrole and imidazole, both these nitrogens have a hydrogen. Okay, so in short, you can remember it like if no hydrogen on nitrogen, if no hydrogen on nitrogen, then the lone pair is not on pi electrons, okay, is not on pi electrons, okay, you can think it like that. But if the nitrogen has a hydrogen, if a nitrogen has a hydrogen, then the lone pair will be a part of the pi electron cloud. It is included in the pi electron cloud. So when you are counting pi electrons, okay, this is 2, I'm counting the double bond, okay, and this lone pair will also be 2. That is how you get 6 pi electrons. 6 pi electrons, okay. So if the nitrogen has no hydrogen, then the lone pair will not be counted as pi electrons. But if the nitrogen has a hydrogen, then the lone pair will be counted into the pi electron cloud, mainly because that lone pair will be on the unhybridized p orbital. I hope you understand it. All right, so if you don't, please rewind and listen again, because this is an easy concept to understand. At least remember that, you know, if a nitrogen has a hydrogen, then the lone pair is included in the pi electron cloud. If a nitrogen has no hydrogens, then the lone pair is not included in the pi electron cloud. Keep that in mind. So here in this lecture note, I have a few more examples for similar rings. You can take a look at it by pausing the video. I'm not going to explain it and keep the video very long. And then furan, once again, is similar to benzene or pyrimidine or pyridine. Why? Because I mean, oxygen, the thing about oxygen is that it is group 6A, which means it has 6 valence electrons. And also it has 2 lone pairs. It has 2 lone pairs, right? It has 2 lone pairs. When you have 2 lone pairs, okay, and if it is sp2 hybridized, that means one lone pair will be counted against the pi electron cloud, and the other lone pair and the second lone pair will be on the plane, okay, will be on the plane, so it will not be counted. All right, so here's the worked example, so you can try it, okay, try and see if you could get the answer. But basically, once again guys, when it comes to oxygen, one lone pair will be counted into the pi electron cloud and the other will not be counted. So every oxygen will give you 2 electrons. Every electrons will give you 2 electrons or one lone pair to the pi electron system. All right, so as you can see, every oxygen will only give one lone pair, so that the overall pi electrons will be 6 pi electrons. Okay, every lone pair, out of the 2 lone pairs, only one will be donated to the will be in line or aligned with the pi electron cloud, so making it only 6 pi electrons. And furan is of course an aromatic compound. All right, with that I'm going to conclude this video guys, so please let me know if you have any further questions. Okay, please let me know if you have any further questions. You guys have a good one. Take care.